recap from yesterday, how many orbitals does the S sublevel have? P, D, and? Right, so it's a pattern. That's the name of the game in this entire unit. All right, there's a lot of different patterns that you're going to want to recognize and to remember all throughout this unit. All right, so again, these are the sublevels, then those are the number of orbitals, kind of like the bunks of where those electrons can be found. And then each orbital holds up to 2 electrons. So what's the total number of electrons the S sublevel can hold?
2.
P?
6.
D?
10.
And F? Okay. Let's talk about the third quantum number. It's called the magnetic quantum number. Its symbol, guys, is a lowercase m, and sometimes it will have a lowercase subscript L, cursive L, like that. All that this does is that this indicates the orientation around the nucleus. Is it on the y-axis, the z-axis, the x-axis, okay? That's the way you want to think about it. Now, it's symbolized sometimes with numbers. 0, okay, there's that 1 orbital. You've got 3 orbitals for P, so -1, 0, +1. You've got 5 for D, -2, -1, 0, and so on. All right, I do not believe, and I've got to double check on this, but we're not going to stress about it now. If we need to know the numbers, we will come back when we review at the end of the school year. We'll go through that numbering system, but I don't believe that is something that that you need to worry about anymore. When I was in high school, I learned about it, but to be honest, even when I was in college, very rarely did I even talk about that. So it's not as big of a deal as it used to be. Biggest thing you want to remember with that magnetic quantum number is it's the orientation about the nucleus. All right? Number 4, our last quantum number is the spin quantum number. Its symbol is very similar to the last one. It's a lowercase m with a subscript s for spin. Okay? It indicates the spin. There's 2 possibilities. You can have a +1/2 or a -1/2. Basically, guys, what that means, the +1/2 is clockwise, and the -1/2 is, oh, look at you, counterclockwise. All right, so counterclockwise CCW and clockwise CW, just a way to abbreviate those. All right. Big idea right here. Pauli's exclusion principle. You got to know it. It's one of your definitions, so there you go. I just defined another term for you. No 2 electrons in the same atom can have the same set of 4 quantum numbers. So you need all 4 of these quantum numbers to describe the most accurate location of the electron. Now, is it possible to know both the velocity and the location of the electron at any time? No, you can know one or the other. What states that? What principle states that? Heisenberg's uncertainty principle. Good. All right. Pauli's exclusion principle, all right, adds on to that. No 2 electrons in the same atom can have the same set of 4 quantum numbers. Again, you need all 4. You need the principle, you need the orbital, you need the magnetic, and you need the spin to really describe the most accurate position of that electron, but no 2 electrons in the same atom can have the same set. All right? And here's why. It all comes back to energy. That's going to be a common theme throughout the entire year. If I gave you guys an option to run a marathon or to stay in bed, the overwhelming majority is going to choose what? Stay in bed. Why? Why? Because we are lazy, right? Myself included. All right, we'd rather use the least amount of energy possible, guys, and that is what atoms are doing all the time. Our next unit is going to be bonding. We're going to be talking about how to make structures and things like that, and it all comes back to energy. They want to be in the lowest energy state possible. So when we talk about electrons that are very, very close together in those orbitals, all right, if they're both spinning the same direction, it's what's called strain. All right, on the molecule, on the system. So by one spinning positive or clockwise, the other one spinning counterclockwise, it's actually lower in energy than if they're spinning the same way. And that's what Pauli's exclusion principle is talking about. It all comes back to energy, right? Lower energy. I would add that in there. That's kind of a common theme. We're going to think about that, and we're going to use that answer all year long. Okay, all year long. All right, so we've gone through the 4 quantum numbers at this point. I believe at the top of the next page on your notes, it says the quantum number pyramid. So here's what we're going to do. All right, the whole idea with these quantum numbers, as we said, is to try to pinpoint as close as we can the most probable region or location that those electrons are located. So what we're going to do is we're going to draw an upside down pyramid in that space. As big as you can make it in that space. Yeah, I guess it could be an ice cream cone. I never thought about it like that. So the other analogy that I used yesterday, or we started talking about, is with electrons, we think about it like if you're describing where you're located. What are some ways or kind of parameters that we can use to describe where we are located? We can use latitude and longitude, but not that specific. Town, city, state, country, county, all that kind of stuff. All right? So that's what this is talking about. But we're going to use that model here for an electron. What's the most broad sense that we can talk about where an electron is located? What's the most broad sense, the broad description we can say where an electron is located? Electron cloud. All right, that is the most broad sense, the electron cloud. Right? Because where is that? Outside the nucleus, okay? Doesn't really pinpoint. It's like saying, okay, you're in the United States. Well, that's a huge area. There's not really much going on. Now we will start with our quantum number. So here's going to be quantum number 1, which is what? Nope. Principal quantum number. What's the symbol for my principal quantum number? Lowercase n. All right, and what does that tell me? That tells me my energy level. So it's kind of what ring around the nucleus are we located. Now, are there actually rings, folks? Right? No, right? Because Bohr's model doesn't hold true. It's just regions, but we think about it like rings, even though they're not really. All right, the next one. Principal quantum number 2, and there's going to be 2 parts to this. What were you going to say? The orbital quantum number. Okay, it's got the lowercase cursive L for its symbol, but there's really 2 parts to it. Okay, there's 2 parts. So I'm going to do this, and I'm going to change up my colors just to kind of label the 2 parts. So what's the first part that the orbital quantum number tells us? Spediff, right? Which are what? Those are called the sublevels or subshells. So I'm going to write this in here, guys. Sublevel. And I'm going to put spediff in parentheses. Okay. But then what else are located within that orbital quantum number that are related to spediff? Not yet a number of electrons, but orbitals. Okay. The orbitals. Right? The orbitals, guys, and they're related to spediff. So I'm going to draw like a little arrow saying, oh, that's going to help guide us to the orbital. So you've got both of that going on. You've got the sublevel, and then kind of below the sublevel you have the orbitals. That's even more specific. Okay? Bless you. Okay, so you've got the electron cloud, the principal quantum number, which are really the energy levels. Then you've got this orbital quantum number, which has sublevels, but then they can be broken a little bit more. The letters tell us and guide us to how many orbitals, how many bunks are there in that. All right, then the next quantum number we have, our third one, is what? That we just learned about? What? Magnetic quantum number. Symbol for that? L, yep. And then the last one, our fourth quantum number, is the spin, and our symbol for that's going to be MS. Okay? So this is showing us by flipping that pyramid upside down, as we go down, we get more and more pinpoint to where those electrons are. Big idea here again, remember that you do not know exactly where those electrons are located. We can either know the position or the velocity, one or the other, but not both. Okay? Any questions?